In this video we'll look at the shortest distance from a point to a line. So in this situation here, if we have a moving object along this path here in direction vector B, then the shortest distance would have to be a line from point P that is perpendicular to that line in which our object is moving. So we can see here that if I were to construct my perpendicular there, the distance from P to R, where R is now being moved to this position here, would be the shortest distance. Point P is known as the, well, not point P, point R is known as the foot of the perpendicular. Alright, so if we were to consider a problem such as this, we have a line here and a fixed point. I'd recommend drawing a diagram first up. So we have a line, we have our point P, the direction vector of that line is the vector 3, -1. Now every point on this line, and we want to work out the foot of the perpendicular, we'll call that let's call it F for the foot of the perpendicular. Every point on this line can be expressed in terms of this equation here, where the x value is 1 plus 3t, and the y value would be 2 minus t. Therefore, the vector from F to P, we want that to be perpendicular to the vector, let's call that vector B there. So we want FP dot B to equal 0. And that will give us an equation which should lead to a solution. So working out the vector from F to P, I'll have the P value subtract the F value, which would give me this vector here. I then dot that with vector B, which is the vector 3, -1. That has to equal 0. Let's simplify that first vector, which gives us this, and then dot that with the 3, -1, which would lead to one equation, one unknown. So we end up with, we've got 12 minus 9t, then multiplying the y component by -1, I'll get plus 3 minus t equals 0. Collecting like terms, I've got -10t plus 15. Let's move the 15 across the other side. Divide by -10. I get the time will be 1.1. So therefore, if I were to substitute that into point F, I'd actually work out the point F. I want to work out the distance, however, and therefore that's the length of the vector FP. So let's work out the vector from F to P by substituting t equals 1.5 into our vector here. And in simplified form it's there. So we end up with F to P is going to be, we've got -0.5 for the x component and -1.5 for the y component, and therefore our shortest distance is in fact the length of that vector there, which will be a half squared, which is a quarter, and we've got 1½ squared, now that's 3 on 2, which gives me 9 quarters. So we end up with 10 on 4. Square root of that is √10 divided by 2. Next example, we have a ship at R, which has left point A, travelling in a direction given by the vector 3, 4. Now we're told that the speed of the ship is 10 kilometers per hour. Looking at that vector there, the speed of that, or the magnitude of that, is only 5. Therefore we need to times that by 2 to get our velocity vector. And therefore, if we were to write an expression for the ship in terms of t, let's do it in parametric form. We'd have the starting position, the x component is -8, and then plus. Now, rather than 3, it'll be 6 times in by t, and the y equation, we're starting at 3, and then once again doubling the 4, we've got 8t. So that will give us the position of the ship at any time t. Now part B, the time when the ship is closest to port 10-2. So I now want to work out the foot of the perpendicular from this point here. Once again, this point here, we'll call it F, will be expressed in terms of our parametric equation here. So let's work out the vector from F to P. So once again, we'd have the 10 take away -8 plus 16, which would give me, now that's going to give me, let's write it down. So 10 take -8, take 6t, and then I've got my 2, take away my 3, also take away my 8t. So I end up with 18 take 6t, and I've got a -1 minus 8t. So now once again, our dot product of this vector and this vector here has to equal 0. Now using 3, 4 gives us smaller numbers, be easy to work with. So I know that 18 minus 6t minus 1 take 8t, the dot product with the vector 3, 4 must give 0. Solve that equation there and we'll get our t value, and that will give us the time when the ship is closest. Last example, we have a point P and a line given in 3 components now, x, y and z. So the coordinates of the foot of the perpendicular. Once again, let's draw a sketch. We've got our point P, we've got our line. Now the direction of that line is given by the vector 2, 3 and 1. They are the coefficients of t in our parametric equation up here. Once again, point F can be expressed in terms of our parametric equation. So every point on that line is expressed in terms of that. So we then need to work out the vector FP, dot that with 2, 3 and 1, and we will get 0. So once again, FP calculated as before, solve for t, and then work out the vector FP, because the shortest distance will be the length of that vector. So similar to the first example.